All right. Hello, ladies and gentlemen. We're continuing today with our talk about earthquakes. So we have answered a little bit already about earthquakes. And so we talked about the fact that there are 7 essential questions that by the end of the unit you should be able to answer. The first 2 we have kind of talked about already. So how do plate boundaries impact earthquakes? We talked about that when we looked at the map of 15 years worth of earthquakes, where they were located, and the fact that so many of them were located at the boundaries of plates, because that is where there is a lot of movement happening, and because of that, earthquakes are happening. We also talked a little bit in our last lesson about number 2, how are stresses in rocks related to faults? And we looked at the fact that when there is tension in a rock, you have a normal fault. And when there is compression in a rock, that you have a reverse fault. And when there is shearing between rocks, then you have a strike slip fault. Today we're going to move on to questions 3 and 4. So if you would make sure that you take out your notes page and follow along as we talk about how to answer the questions, what are characteristics of different types of seismic waves and how are epicenters determined? All right, we're going to start with a review. You just had a test over this shortly, not too long ago. A review real quickly. This diagram was even used in the test that you took the other day. So we have the crust, which of course is the outer layer of the earth. It is rocky, it is brittle because it is hard and relatively dry, except obviously we're under the oceans, but it is hard, and so it is quite brittle compared to the mantle, which is much more plastic-like. It's almost like a liquid, but it's not. It's kind of like a solid, but it's not. It's sort of somewhere in between where it can kind of stretch and pull, but is not completely liquid. Then you have the outer core, which is absolutely molten liquid rock, right? Or metal, actually, not so much rock, but liquid metal. And then the inner core is completely solid. It's under so much pressure that even though it's hotter, and therefore we would think that it would be a liquid or possibly even a gas, because usually as things get hotter, they turn from a solid to a liquid to a gas. Instead, the inner core is solid because it is under so much pressure and becomes so dense it can't liquefy. All right. Seismic waves from earthquakes actually have helped scientists to try to determine what these different layers are like, and the fact, which ones are solid and which ones are liquid. We're not going to get into a lot of detail about how they do it in this particular unit. Perhaps later on in your learning career, you will encounter that a little bit more. We're going to talk a little bit about how scientists recognize that earthquakes have happened, how they kind of take in the data from earthquakes. And we're going to take a look at 3 words that sound an awful lot alike. One is seismograph, one is seismogram, and one is seismologist. We're going to talk about the difference between them. And to kind of help us do that, we're going to use a video. Whoops. We will come back to this slide here in just a couple of minutes, so don't panic if you didn't get that filled in. But we're going to take a look at a video that talks about seismographs and seismograms, and specifically how a seismograph works and how it's different from a seismogram.
How a seismograph works. A seismograph is an instrument used to measure the movement of earthquakes. A weight is suspended in a way that allows it to remain still when the ground moves. Most modern instruments use an electromagnetic mechanism for this. A writing instrument is attached to the weight, allowing it to record the movement as it happens. The word graph refers to the writing action. Most modern earthquake monitoring uses seismometers, not seismographs, and record the movement of the Earth digitally, or output the data to a seismogram, a printed version of the wavelengths on a large drum. These wavelengths that represent Earth's movements are so small that in order for scientists to study them, they have to be amplified.
All right, so that was a pretty brief video. Didn't go into a lot of detail, but hopefully it gives you a little bit of an idea of what a seismograph and a seismogram are. So in your notes here, a seismogram, of course, is an instrument that measures and records the details of earthquakes. And you got a little bit of a visual in the video of how that worked. It helps scientists to be able to figure out the strength of the earthquake, depending on how wide those markings are. It also helps to show how long the earthquake lasted, what was its duration. Did it last for a few seconds? Did it last for a minute, 2 minutes, 5 minutes? Would be a really bad earthquake. A seismogram is the actual written part that the scientist gets from either from the seismograph, and then the seismologist is the scientist who's doing the studying of those things. So the seismogram is basically the instrument that is being used. The seismograph is the paper recording of it, or the written recording of it. Seismologist is a scientist. All right, so we're going to take a look. When an earthquake happens, we know that energy radiates out from the point where the earthquake happens. And we know from our oceans unit that that energy travels in waves. And when we talked about oceans, we talked about how that energy traveled through water, creating waves, because energy always travels in waves. Well, the energy from earthquakes also travels in waves. We can't see it quite the same way that we can see ocean waves, because, well, water is liquid and it moves, so we can see it. Solid things tend not to move in quite the same way, so we can't always see the waves as they're moving through the earth. There are a few different types of waves, actually, that will come from just one single earthquake. The first type of wave that we're going to talk about is called a P wave, or it's also known as a primary wave. It is the first type, or it is the first wave to arrive at a seismic station, a place that measures the movements of the earth. These stations are set up all over the world. And so these are the places where seismographs and seismograms are set up so that scientists can detect the movements of the earth. And the P waves are the first waves that arrive. They're the ones that start kind of making those first marks on the seismographs. So the P waves are able to move through solid material like rock. They're also able to move through liquid layers of the earth, like down into the mantle and into the inner core, into the outer core, excuse me. So P waves can travel through both liquids and solids. We'll see in just a moment, not all waves can do that, but P waves can. They travel very fast. They can travel through both liquid and solid. They're what we call a body wave. And next week we will, or next time we have class, we will be creating a diagram to help us be able to differentiate between these different kinds of waves that I'm going to introduce you to today. We'll get into a little bit more detail with them in our next class, with both a diagram as well as doing a couple of demonstrations of how these waves work. But for now, we're just going to do a little introduction. And the last thing that you kind of need to know about the P waves, or the primary waves right now, is that they shake the ground back and forth. It's kind of a pushing and pulling motion, where you have, as you can see in this diagram over here, you can see there are places where it gets compressed, and there are places where the rocks get stretched out or extended. And so it's kind of a push and pull type of wave. We will demonstrate a little bit of what that might look like in our next class, but just know for now that it's kind of a back and forth push and pull type of thing. The second type of wave that we're going to look at are called S waves. They are also known as secondary waves. They move much slower than the primary wave or the P wave, much slower. They are able to move through solid layers of the earth. So they can move through the crust. They can also move through the mantle, because the mantle is not completely liquefied. It is kind of a plasticky, stretchy type of solid. So it can move through both of those layers. It cannot move through the outer core. The outer core, again, is liquid, and so S waves are not able to continue their vibration or their movement of energy through the outer core. They are also known as a body wave. Body waves, essentially, the P waves and the S waves, these body waves, travel through the earth. Okay. And in this particular case, with the S waves, again, they're slower. They move rock particles kind of either side to side or up and down. All right. And you can kind of see that in this diagram down here at the bottom. The energy itself is moving to the right, but you've got movement of the earth going up and down. So the earth is not moving forward like the energy is. It's just moving up and down. It's a little bit like an ocean wave, but we're going to see a different kind of wave in a minute that is a little bit more like that. We'll take another look at this diagram to the right here in a little more detail in a future class as well. All right, let's take a look at how we can graph P waves and S waves. You'll notice we have a line graph here to the left, and a graph is often used to determine how long it takes for different waves, P waves and S waves, to reach different places or go different distances. It helps scientists to be able to determine the place where the earthquake started or originated from. When an earthquake happens, sorry about that. When an earthquake happens, we almost never know exactly where it started until we start to do some calculations. We might have an idea of, what populated places it was close to, but if we want to know exactly where it happened, to be able to study it and to gain some information from that, graphs are one way that scientists can try and figure out where it started. And so you'll see here in the graph, it says, what would the difference in travel times between the first P wave and the first S wave be if the seismic station is 1,500 miles from the epicenter? We're really going to learn what that word epicenter is all about in just a few minutes. But you can see here that if the seismic station is 1,500 miles from the epicenter, if we go up from the 1,500 miles, we see that the P wave took just 5 minutes to get to that particular station. The S wave took 9 minutes to get to that station, so there was a 4-minute difference. You can see that as the P wave continues to travel, the S wave actually slows down further and further. And so how far away the P wave and S wave are from each other can help a scientist to determine exactly where did that earthquake start. Let's talk for just a minute more about these seismic waves. So surface waves are a third kind. We've talked about primary waves and secondary waves, or P waves and S waves. Those are body waves. This is a different type of wave. Surface waves are not body waves. They only travel through the crust. They don't travel through any other layers. They always arrive last, so to speak. They arrive after both the P and the S waves. They are the waves that are responsible for all of the destruction and damage that happens in an earthquake, because they are the ones that are like traveling across the crust, across the surface of the earth. The P and S waves are traveling down through the layers of the earth, and therefore they do not tend to cause the destruction that we see during an earthquake. It is the surface waves that are the ones that are causing the destruction. You'll see there are two types of surface waves. There's the Rayleigh wave, and there is the Love wave. Interesting names. They actually happen to both be named after people and who helped to discover them. But the Rayleigh wave kind of moves in a circular motion. In a lot of ways, it's very much like an ocean wave. In that the earth particles are moving in a circular motion as the energy moves through. Sometimes you can actually see, if it's a very violent earthquake, you can actually witness the kind of rippling effect for a few seconds of these Rayleigh waves. The Love wave actually goes like back and forth across the surface of the earth. So instead of kind of going up and down, the Rayleigh wave goes back and forth across the surface. So if we follow this one here, it's not going up and down. Instead, it's kind of going left to right. The last thing one of the last things we want to take a look at today is something called the focus and the epicenter. The focus is the point where the earthquake actually originates. That is usually down inside of the crust. It's not right up at the surface where we walk around and things. The place where the actual earthquake happens, where those rocks actually get caught on each other and then actually move and jerk at the last moment after the energy has built up, that focus is underneath the ground. And so the focus, we can determine how deep underneath the ground it happens. And you'll remember when we watched the video about the 15 earthquakes, or the 15 years worth of earthquakes, the colors of the circles change depending on how deep that earthquake happened. Where its focus was located down in the crust. The epicenter is the point up on the surface where we walk around. It's the point on the surface that is directly above the focus. All right. So the focus is where the earthquake actually happens. Nobody actually lives at the focus because it is underneath the earth, down in the ground. The epicenter is the surface of the earth right above the focus. The epicenter is what we often talk about because we live on the surface of the earth. So we tend to be a little more concerned as a general citizen of the world with where the epicenter of an earthquake takes place. And so scientists use a method called triangulation in order to try and determine where the epicenter actually is. Where did this earthquake happen? And so scientists use these seismographs that are set up all around the world, and they take the information from 3 seismographs. They determine how long it took the waves to get to that seismograph by measuring by measuring the length of time between when the P wave arrived and when the S wave arrived. That helps them figure out how far away it was from that city, but that could be in any direction. So when they draw a circle around the city showing how far around it was, or away from the seismograph to show how far away it was, if they use 3 of them, eventually those 3 circles are going to intersect at one point, and that becomes the epicenter. We'll talk a little bit more detail about that at a later date as well. For now, you may put your notes away. Make sure that you have filled in all of the notes up to the point where it talks about determining the epicenter. And in our next class, we're going to talk a little bit more about these different kinds of waves and eventually talk about a little bit more detail about how it is that scientists figure out where the earthquake happened. Where is that epicenter? Have a great day, everybody.